everyone. Welcome back to my math teaching online today. Um, Today, I'm so exciting to introduce to you a new lesson about the shell method in the same topic of volume of solid revolution in calculus course. This is a fascinating topic. Maybe my favorite topics when I was learning it 20 years ago in university. Back on the time when I was learning about it, we so busy with on the like the 4 or 5 courses, other courses. I didn't have a chance to research about the deeper into this topic, and we just learned through it very quickly and try to so back on those times, this topic is still very abstract, right? When we don't see the computer software generate the volume in the three-dimensional image for us to see. The advantage nowadays you learn with on the advanced technologies and on the course online on the YouTube like that, you'll be able to pick it up, I guess, a lot more easily. Anyway, before I get into the lesson, I would like to talk a little bit about my course online and allow me to give you 1 minute to for me to advertise for my online courses, right? Um, I think online education now is in the reform education of this pandemic difficulty, but also it's not a bad idea for future young generation learner who want to understand more and get deep into the um, academic field, and they want to learn more and more, right? Knowledge has no border, has no limited border. So anyway, it's a good side, right? Also, my course, you can get into 2 ways. One is following me on, if you want to buy a full set of course. The full set of course will including the 54, at least for each course, I will produce at least 54 video lectures. It depend on the topic, depend on the course as well, but roughly generally speaking, um, live video, face on face like this for my explanation, really explain step. And the advantage of buying the full set of course is they are connected well and have on my lecture notes, and sometimes I put it in the MS PowerPoint presentation, right? Beautifully and explain clearly step by step to stand out to you online course, attract your thinking. Secondly, if you don't want to buy the full set of course, you can follow me on my website, wordpress.com, under the http mymathteaching.ca. I wrote it here. If you go to this website, math courses online.teachable.com, you can purchase my courses. The first introduction to calculus course has been published so far. This course I am creating right now, we're not done yet, and I still need some more time to finish it before I can publish it. So there are 2 ways. Now, if you get into this website, mymathteaching.ca, you learn weekly free online education from my teaching. But it will be, I will post it week by week, right? So it let you learn a piece of it once at a time. Now this is free online education. You can take advantage of that if you have time, right? Now everybody have to make time for something if you like it, and if you think it benefit you in the future. Sometime we have to satisfy our time right now to invest for our future, or we have to select which one is more important to do right? So it's on up to every individual person. But I'm just advertising for my course. I think that compared with the labor, I work 7 hours a day, 7 days a week, more than that, to develop one course with on the live lecture like this. It's nothing if you have to pay a few hundred, to be honest with you. But we know that everybody in the difficulty now, so it's just a little bit support of, of our audience around the world, so we can keep going to build our course online and give you free online education. Um, so we all can contribute it and like give us a little bit support uh, for us to keep going to be able to develop the course online for you, because we have to live and we have to eat and we have to live a simple life. So I just, for my course, I provide weekly online free education, and I just ask for a little donation, not much, right? A few dollars or something. And to help us to be able to keep our energy going and develop online course. So that is about my website. Now I'm going to get into the lessons, right? So the lesson today, you can see that on the board, I draw a curve, look like this curve, and I call this curve is an fx function. But and inside this curve, I have two cylinders, right? One inner and one outer. Now, why it like that? Let's talk about the cylinder first, okay? Now, so the lesson today, I would just talk about the concept of the shell method and give you a good solid definition of what the shell method means, what the shell method means to you. So to reduce the abstraction of it, right? So when we do the shell method, we're talking about the cylinder. Let's look at the cylinder of the paper towel. I hold it in my hand, right? Actually, okay, let me think about another way of connect the concept to you. If you have an onion, right? You know that you can peel off the skin of the onion, and then you peel one after another layer inside another layer, right? Surrounding the onion. So you peel off the first shell, you peel off another shell, you peel off another shell. The whole cylinder, the whole onion is a volume, but each shell, right? Each shell you peel it off. If you stack it together, it's become a volume, right? And that's why we call it shell method. Here you go. You see like the imagination and the reality, right? The onion have the shells, and if you peel off the shell of an onion, each of them stuck together, it become an onion. So the same idea, and that's why we call it shell method, because it have a layer, right? A shell, one after another. You can peel it. Now, the same idea for this paper towel, right? Let's look at this cylinder shape. If I take off, this is the first layer, right? And then if I keep remove it, just like removing the shell of the onion, right? But if I keep removing it, this cylinder gets smaller and smaller, right? But if I want to build it, I stuck them together. I stuck them together by the surface area, right? And it become a volume of the cylinder here. Now, let me take up one shell, right? One shell like this. So if I take up one shell of this paper towel, and this one shell here, the one shell here, actually a surface area of the rectangle, right? But if I close this rectangle back, I got the cylinder, shape of the cylinder. If I cut it, open up, it is a surface of rectangle, right? It is a surface of rectangle. So if I form it like, I connect them like this, it will become a cylinder. But once one layer like this, not going to form the volume, right, of this cylinder. because it's so thin, right? To form this, become a volume, I have to stack so many shells like this, right? One after another, look like I generate, right? I revolving around the y-axis. So I stack them together. I stack all of this shell together to form a cylinder, right? So you see like one after another of this surface area of the cylinder will form a volume. So what is the volume of the cylinder? The volume of cylinder will build by stacking all of this shell together, one after another, as many as of them, right, around this, like a perimeter around, to form the volume. So the volume of it is actually the thickness here, right? Without this thickness from here to here, you only have one thin shell, doesn't have a volume. But if you want to form a volume, you have to build it, right? You have to generate it, revolving it, right? Build it one after another layer, until you form a thickness from here to here. So you can visualize very well from my demonstration, right? So from here to here is the thickness of this shells of the cylinder, of many cylindrical shells stacking up together to form a volume of this cylinder. And the idea is very much the same like in this method. But in this method, we slide this line around, revolving around the axis, and we slide them in a circle. And that's why shape, that's why you call it this method. And we stack them together, right? That's this method. But today we're talking about the shell method. And these two techniques are totally different, right? Because this is from the surface area, right? We're talking about one surface area, stack them together and to form a volume, right? So in this method, we're talking about the bottom, the area of the one slide, right? Pi r squared times with the height to form a volume. The shell method, we're talking about the surface area of one shell, like this shell, like this one, right? Of one shell, surface area of cylinder, and we build them by the perimeter. We keep doing it. We put stacking this onion shell together to form an onion or to form a cylinder. Now, however, I'm going to explain to you, our object in the real life is not the cylinder. It could be, right? But it could be another shape. Just like the shape here, like a hat, right? I draw it on the board. But the idea, we still form it by the cylinder. However, this is not a fixed cylinder because this cylinder have the fixed height as well as the fixed length and width. When we open it up, right? This is length, this is height, or you can call it width, whatever. And on the shell have the same size and the same shape. And you just stack them together, and it become a cylinder, right? But our object could be something like this, right? But the idea is still the same, except that the height of it will change according to the function. So here you can see the height is short, and then when you build it, the height is longer, So as long as you have the simple idea of building the shells together, but each of the cylinder here, one after another inside, is not the same shape, it's not the same size. It's bigger and bigger outside and smaller inside, or maybe bigger than inside and then get smaller outside, depend on the object, right? So as long as you have a height of the cylinder is changing and the radius of the circle here is changing, then you can shape the object by different shape, depend on the function. So that is the idea. But to explain the concept at the beginning, we have to talk about the same size, the same shape, and to form a cylinder for you to see. But when we apply this concept to this object, you can see each layer of the cylinder inside here will be changing the shape, right? The thickness will build, but the shape, the size, as long as the size is shaped according to the function, we will have the shape of the volume of a solid revolution, not just this cylinder. And it could be any shapes we want, right? However, the way we generate is still using the cylindrical shell method to build the volume. And that's why we call it shell method. Okay, so I hope that is a little bit like clear to you. The abduction is gone a little bit, right? But let's get into the diagram and you will understand this topic better, even better, okay? So here, let's look at this shape, right? But before I do that, let me write down the important concept we need to know, right? First, let me read this today so that I'm not wander around. I put it two things I would like to explain in this lesson. The first thing, I would like to give you a definition and explanation of the concept as much as possible. Second, I will give you the formula and identical features between this method and the shell method. So you can distinguish between the this method and the shell method thoroughly, so you don't mix up between these two techniques in the future, right? When we perform the task. And that's why I would like to spend time in this lesson to explain about the concept of the shell method rather than problem solving. After we understand this concept clearly, I will get into the next lesson, which is we will have a problem solving. So let's talk about the volume. So the volume of the shell method, right? The volume of the shell method equal surface area of a cylinder time with the height. So surface area is 2 dimension, right? Time with the height is another 1 dimension to form a volume. And this is the formula for all the objects, right? So now let's talk about the surface area of cylinder and its height. So let's review about the surface area of the cylinder. This is the cylinder. So now I'm not talking about volume, right? I'm talking about surface area first. If this is the cylinder, if I cut it open, right, then I get the surface area of the whole cylinder here, right? The whole surface around. If I open up, and that it become a rectangle. So the surface, this area of the cylinder actually is just the same like the surface area of a rectangle, where the top is the height, the length, and the side width here is the height or the width we call in the rectangle, right? If it is a rectangle shape, we call this the length and we call this the width. So to find the surface area of this cylinder, all what we do is cut it open up like this and use length here times with the width here. Then we can have a whole surface area of the cylinder. However, we have to talk in terms of the shape of it. So if I cut it open, this length here on the top actually is the perimeter of a circle, right? So let's talk about, so I'm going to say here volume equals surface area. Now I put in the short form surface area of a cylinder times with the height. but the surface area of cylinder will be equal length times width, right? And you see that I demonstrate, right? Length times with the width here, and the width turn out to be the height, right? So I'm going to substitute this height by the width, right? And now I'm talking about length times width, right? I haven't talked about the volume yet. I just talked about the surface area, right? So length times width, which is the surface area of this cylinder when I cut it open up. Now, if I close it, the length here become, and I have to talk in terms of the shape of it because we're not going to cut it open up, right? So the width of, the length of it here turn out to be the perimeter of a circle, or we call it circumference, right? So this is around, the side of this is around the circle, and it become a circumference of the circle on the top. The same like circle at the bottom, right? But we're just talking about one length. So it's just one perimeter of circle, one circumference. So I'm going to substitute this length here, volume equal the length here. Okay, actually, sorry. What I'm going to do, I'm going to just talk about this part first, right? So this will be length and width to form a surface area of cylinder. This still have a height here, right? This height is still there to make a volume, right? So the length here will substitute by the perimeter of a circle, which is 2 pi r. The formula to find the perimeter of circle or the circumference is 2 pi r. So I just substitute one by one step, right? So I substitute the length here by 2 pi r time with the width, right? I still have to have the width. So the length here turned out to be 2 pi r. But what is about the width here? The width here is the height of cylinder, right? The width here is the height of it. So I'm going to substitute the width by the height of the cylinder. Remember, this height is different, right? This height is the height of the whole volume outside from here to here. And they could be different depending on the shape of the object, right? But in the cylinder, this height outside here is the same like this height inside here, right? And so maybe I should mark this in height 2 and this in height 1, right? Because they're not the same, okay? So this is just from this one here is the surface area of cylinder, time with the height to form a volume, right? So I am going to, we'll write down here, okay? So volume equal 2 pi r is the perimeter of the circumference time with the height and time with another height to form a volume outside, right? And I call this the height 2, okay? So now let's talk about the shape here. So let's say if I have a curve like this, I'm going to find the volume of this object, right? And I'm going to do it using the shell method by building the cylinder shell, right? Using the cylindrical shell and stack them one after another. In here, I just demonstrate 2 of them, but it should be so many of them like this paper tower, right? Okay. So let's say, now we also realize one more thing. I want you to realize that if I have a curve like this and I call this a function f of x, right? It means I have a function of f of y in terms of the x, right? But different from this method. This method is you generate this volume around the x-axis. But in the shell method, if I don't put this cylinder this way, right? If I just stand it up like normally like this, right? Then the way you generate the shell method technique itself is generate revolving around the y-axis and not the x-axis. And therefore, as long as I have a function here, y equal x to power 3 or y equal square root of x, whatever the shape of the function here is, I don't have to reverse the function, right? So the shell method, if I generate this cylinder in this standing up way, then whatever the function is revolving around the y-axis. So I'm going to mark it as a note, right? So keep in mind, I put sideward here. Keep in mind, we generate about the y-axis if the function is y equal f of x. So if the function is y equal f of x, not x equal f of y, right? So our function is f of x, not f of y. So what if our function is f of y? What do we have to do? We will generate revolving around the x-axis. In that case, we will put the cylinder this way, right? And we generate around the x-axis. And in that case, we have to reverse the function. But the first lesson, we always make symbol first, right? We don't want to explore anything else. So the first, and why do sometimes we generate along the y-axis and sometimes we generate along the x-axis? Because depend on the shape of the object, right? And that's why we have to learn on the technique so that we can apply each of them based on the shape of the object. Sometimes the shape make it easy to make the cylinder lie sideways like this and generate along the x-axis. Sometimes the shape of the object requires just let the cylinder standing up like this and generate revolving along the y-axis. That's the idea, okay? So now let's talk about the formula now. Continue with the formula here, okay? So keep in mind that none of them are fixed number. Remember, we learned that calculus is the rate of change. So all of this radius here and the height here is the subject of change. It's the object changing, right? That's why we call it rate of change. So if you look at, make observation of my diagram here, right? If we build the shell of the cylinder, right? Obviously, you can see that the first cylinder outer here is bigger than the one inner here. And as long as we build the cylinder along the shape, we're going to have a big one and then get smaller, smaller according to the shape of the function, right? And therefore, none of this cylindrical shell has the same size or the same height or the same radius like this one, like my paper towel, right? Each cylindrical shell here have a different radius and have a different height. It's changing and shaped by the height of the function as well as the width of the function, right? So let's talking just about half. Usually we always talking about half of the function, right? When we build it, become a whole thing, but actually it's the half of the function. Let's say the function from here to here. This is the function, right? Let's talking about half shape here, okay? Now, you also realize, maybe I'm talking about left one, okay? Not the right one because I draw it here. So the radius from here to here, the same like radius from here to here, right? And for the radius, I mark from here to here. And actually, the interval we're going to revolving it is A to B. So what is the length of A to B here? How you can imagine? Actually, A to B is this length here, right? This radius here, okay? So the A to B here is the radius, right? And an object of chain, this radius is from here to here is the radius. Now, how do we find this radius? And because it's along the x-axis, so I'm going to call this is the delta x. Okay, so this is the delta x. And this radius is built based on the big radius from the zero origin here all the way from here to here. We call it R2, right? Minus, as long as we generate from inward to outward, right? And that's why we call it generate from inward. This cylindrical shell will be generated from inward to outward, right? You can see that I build it like from inward to outward. So the radius is the difference between R2 minus R1, and that's why we call it delta x, right? So the delta x here actually is the thickness of the shell, which is from here to here, thickness of the shell, right? And the thickness of the shell here is along the axis, and that can be calculated by the difference between R2 minus R1. And you can see obviously, right, from here. Let's say from here to here is R2. Then the way you build, you're going to build, at first you build a little bit here and then getting bigger and bigger, right? So as long as you use a whole R2 here, subtract this from here to here, from 0 to this 1, this is R1, right? So then you get delta x. The same like you look in here, if you use R2 is from here to here, right? You subtract R1, the radius of the inner cylinder. So the R2 is the radius of outer cylinder, big R minus small r inside the cylinder. So this from here to here is R2 minus this part, you get delta x here, this one here, right? So you can see our thickness generate build on from inward to outward, from inward to outward, and delta x here represent R2 minus R1. The big radius subtract the small radius to get the difference between them, right? So as long as we keep going, R1 getting bigger and bigger until the distance between them, the gap between them is 0, right? R2 minus R1. Okay, so that is about the radius. What about the height? So I'm going to substitute this radius here. I'm going to say volume will be equal to pi, and our R is delta x, right? I'm going to substitute because keep in mind that the radius here is the object of chain. It's not a fixed radius. So I'm going to substitute R here is delta x, right? Which is the same like R2 minus R1. What about the height here? The height here is, okay, what about the height here? The height here, height 1 here, right, is the subject of changing as well. So this height of the cylinder, right, from here to here, can be long like this, or can be shorter and shorter and shorter near to the end of the corner here, right? So this height getting smaller at the end and getting bigger and bigger, taller and taller when we go inward, right? When we go outward, it's getting smaller by the shape of the function. So actually the height of this function is what? The height of this function is the y-coordinate of the function. And the y-coordinate of the function, right? If you're talking about the height from here to here, is this y-coordinate, right? You can see that, the y-coordinate right here. You're talking about the height from here to here, the y-coordinate is here. You're talking about the height here, the y-coordinate down here, right? So actually, this height is what? I can substitute it by the function, because this height is changing according to the function f of x. So the height here is just a function f of x. So I substitute into it, right? Okay, I hope that is clear. So what else do we still have? We still have the height 2 here. Let's talking about the height 2. Also, keep in mind that the fx here is the height 1, but what is our height 1? Height 1 is the subject of change from height 2 minus height 1, right? So let's say you want to find the length from here to here, you use y2 minus y1, right? y2 minus y1. So height here is, we call the delta y. And delta y equal y2 minus y1, right? y2 minus y1, y2 minus y1, y2 minus y1. So that's the delta y. Okay, now, what about this one? What does that mean? So here, we're just talking about the surface area, right? Our surface area is this one. This one is surface area of a cylindrical, right? Cylinder. But what about this? This is delta x, the thickness, right? When we time with this thickness, then we form the volume, because volume is 3-dimension, right? So what is the thickness of this? The thickness of this is actually the delta y here. Delta x here, right? The thickness of this is the delta x here. How do I explain this one? I'm missing what 2 pi r. Okay, so our r is the x coordinate, right? Because we're talking about r here, but actually r here is the x coordinate. So actually, this one should be just the x coordinate. The r is the subject of changing radius, right? Based on the x coordinate. If we're talking about the surface area, so this r is the x here. But this height 2 here, we're talking about the thickness of the cylinder to form a volume. Remember, this thickness is the many layer, right? Many layer of this surface area. So if we have 1 layer, we time with 1. If we have 2 layer, we time this with 2. If we have 3 layer, we time with 3. We have million of layers, we time with million. So actually this delta x thickness here is the many layers of this surface area. And that's the way we build the shell method, using the shell method, okay? Now, when we do this in terms of not rearranging some, we don't add this on the surface area together, because if we use that technique, it will be take a long way, right? Why don't we use iteration, right? We already learned how to iterate, and we know that our thickness, if we iterate from inward to outward along the x here, right? So we can use the iteration. So this delta x actually will disappear when we do the iteration, because we're going to replace this delta x here. If we use the iteration technique, we generate from A to B here to build the thickness of our shell, right? Cylindrical shell. So this delta x here, actually the radius R2 minus R1 here. And we generate from the interval of of this interval a to b. So therefore, if we put in this interval formula, it will be like this. From A to B, right? We're going to generate from here to here, from inward to outward, right? To form the thickness of the surface of cylinder. So we generate from inward to outward from the interval A to B, and we're going to build the thickness of this cylindrical shell. Inside, we have a formula of 2 pi r, but I'm going to substitute r by the x coordinate, right? Time with f of x, and we generate it from A to B. And because this is the function of dy in terms of, of y in terms of x, so we still do the derivative, antiderivative of dx, right? Now, keep in mind, this x mean R2 minus, what does that mean? Okay, R2 minus R1, that is the x. And keep in mind, this fx here is the height, right? And which is mean y2 minus y1. So that's the understanding of this formula. So now I'm going to summarize, and I'm going to talk about what if we generate not just one function like this, all the way from here, right? Let's just look at half the function. We're not, and this is generate a revolving along the y-axis, right? So what if we don't generate one function like that, but if we generate two functions? So I will show you the picture of two functions, how it look like. And let me, okay, let me, sorry, I'm doing, okay. So let me talk about the formula. I'm going to write in one for one function. So this picture is, I'm talking about the one function, right? So this picture is one function. So the formula, right? Now I'm going to give you the formula, okay? The formula of it for one function, we're going to generate from A to B, from inward to outward. If we're talking about for revolving about the y-axis for what shell method, right? This is revolving about the y-axis. So, and don't confuse, right? Don't reverse the function, even though we're revolving about the y-axis. Now, in this method, if you're talking about revolving about the y-axis, you have to reverse the function. But in shell method, we don't. We don't reverse the function, right? We still generate along the axis here, but revolving the y-axis. So the formula is the perimeter of the circle, or the circumference, times with the height, right? So our perimeter will be 2 pi r, but our r is actually the x here, right? Time with, so 2 pi x time with f of x and dx. So that is, we're talking about the one function, right? Now, sometimes might leave it in terms of r so that you can easily to remember the formula of the circumference. So I just leave it at r here, but keep in mind our r is the x actually, right? But that is how it look like, 2 pi r times f of x dx. So here we're talking about a one function. So that's the formula of the shell method, okay? Now let's talk about the two functions. Okay, so I might have to erase some of the board here, but I'm going to give you the idea today for the this video. I'm not solving any problem, right? Let's just look at the two function here for me. Now, if I revolving so this is the picture of the two function, right? I draw it already, I sketched already in order to show you. Let's say you have a function look like this, right? Now you know that is always mirror, right? Mirror shape, right? Because we will form this, right? This is when you open it up, right? When you form it, you close it back, right? So let's talk about halfway here from here to on the right hand side, right? If we have two functions, let's say you have the first function, we call it h of x, and we have a second function this way, we call it f of x, right? So we're going to generate the volume of this solid revolution using the technique of the shell method. And that's why I draw the cylinder here, right? Cylindrical. And of course, the cylinder is going to have so many layers, but I just demonstrate by one cylinder here, right? One shell here. Actually, it's stacked up by so many shells. And as long as we generate from A to B, we generate the interval from A to B here, right? So this region lies between A and B, right? And form it by the two functions. The first on the top, we call it h of x, and the second function down here, we call it g of x. So if we have the question asks us to generate the volume of a solid area under this region between the two curves, then between the two curves here, then what do we do? So our formula to do this will be volume equal integration from A to B, right? And we're going to use the perimeter of the circle here, which is still 2 pi r, right? 2 pi r, but keep in mind the r here is the x, right? The x coordinate, right? 2 pi r or 2 pi x, whatever you want to put it in. Let's put this here a little bit underneath so that you will see, right? Time with, so instead of f of x like we do in one function, this f of x will be delta y, which is you will time with f of h, which is this function, minus this is h of, sorry, the h of x, right? Minus f of x. So this is the first function minus the second function so that you get the area of the region you want to generate. And you're going to apply this formula and dx. So that's it. That is about the shell method. Now, why it looks so complicated and the concept is why so abstract that even though now I try to explain it in details to you, I still find it challenging of explaining in the way that make it very clear as possible, right? But I try my best. I don't know if you like my video or not, but that is what the way I explain and I try my best to explain. And I love this topic, actually. I do love it, right? So this is in the way that you generate the region between two functions. So on what you substitute the f of x here, this f of x for one function by this difference between the above curve, which is h of x, minus the below curve f of x. And you use a surface area of cylinder, which is 2 pi r times with our h, and our h is turned out to be the h between changing between these two functions. So here is the h of h1, h2, h3 according to x1, x2, x3. And the way we build it, right? We build this shell, we stack it from inward to outward along the axis for this interval from A to B to build the thickness of our cylindrical shell from here to here. This is the interval from A to B, right? So you see that we stack so many surface area together, right? But keep in mind that our surface area is changing, have a change in the radius. So this here, it actually is R1, R2 minus R1. And this height here is the height 1 minus height 2, or the function, right? The function h of x minus the function f of x. And the delta x, the thickness here, is we generate, because we generate from inward to outward, so therefore we have an interval of iteration here, right? From A to B. So that is, I try my best to explain to you about the complicated concept of this topic, right? Okay, so now when we get into a next lesson, which is how we solve the problem, then you will get more and more understanding. You will comprehend it very well if you follow me the next lesson on the YouTube for the next lesson, because all my lessons are well connected together, step by step. Okay, so this is just explanation of what the shell method look like and how we do it and what are their formula for generating. If we have one function underneath, generate the region under one function and generate the region under two functions like this. Okay, so now I'm going to so what is the I'm going to talk about the third thing today. I'm going to mention just quickly, right? What is the difference between the formula of this method and the shell method? So the third one, when we talk about the differences between this method and the shell method. What is the differences between two of them? One is this and one is shell. What is the differences between them? We're going to talk about that, okay? So let's divide the bar here by 2. Let's divide this bar by 2. So here is a shell, and here's a disc. Okay, so the formula of this method is using the area of the circle, right? Volume equal area of circle, volume equal area of a circle times with the height. Or you can call it the length if you lie it down, right? I would prefer calling it length because we lie it down, right? Length. Now for the shell, volume will be equal surface area of a cylinder, right? Time with the height. So you can see that the two things are different, right? One is using the area of circle and one using a surface area of cylinder. What else do we see? In this method, we revolving around, about the axis for the function f of x, right? That's the second thing we're talking about. So this is the first thing in the shell. We're talking about revolving about the y-axis for f of x, right? Or y equal f of x, whatever. If we're revolving about the y-axis for this method, right? Then reverse the function, right? Reverse the f of x become x of y, right? Become the function f of x become y of x, right? No, sorry, what I'm doing, become x of y function. So let's put in the way, like look like this, f of y, right? If we're talking about f of x, then we change it, become f of y. So for this one, revolving about the y-axis for f of x. So if we're talking about revolving about the x-axis, then the function f of x, we have to change become f of y, right? So if we're talking about revolving about the y-axis, we keep the same f of x. We're talking about revolving the x-axis, we have to talk about f of y. And the reason, as I told you already, if you put a cylinder standing up like this and you generate it revolving about the y-axis, nothing change. But if you want revolving about the x-axis and depend on the shape of it, then we slide it down like this. At that time, you generate revolving about the x-axis, right? So that's, you have to put the cylinder sideways like this instead of standing up like this, okay? So that's the differences you found between them. Now let's talk about the formula. So the formula for the shell volume will be equal A to B 2 pi r times with f of x. I'm just replacing this 2 pi x, okay, times f of x dx. Also, another formula will be generate from A to B 2 pi x times with and let's talk about delta x here, time with delta y, and that is in terms of the two functions, you will have 2 pi delta x time with h of x minus g of x, or whatever you want to call it, right? And that don't like the way I organize it. That's look like minus g of x dx. Okay, now I'm not going to write out the formula for this because you all know that the formula for this one. Let me just write it down here. Formula of this one will be generate from A to B pi r square but our r we substitute by f of x square dx, right? And if we have two functions, it will be a and b pi f of x minus g of x on of the square dx. So that's the formula for this method. And this is the formula for the shell method, right? If we have two functions, and if we have one function, this is the formula. So I hope that this gives you at least some basic foundation of idea about what the shell method mean and what this method mean and how are they different. Then the next lesson will get into problem solving using the shell method. So I hope you enjoyed my video today. I found it hard. Like I actually I'm not feeling that I give you a very good lesson, but maybe not bad. But maybe I should try to record another tape. But sometimes I'm getting tired if I have to change one after another. But this is I try my best. So maybe I will keep this video and show you. If I have more energy to give you a better lesson, I will try to do it. But I will save my energy to the next lesson, which is application of it, solving it. I want to give you the whole general idea before I get into the shell method. I don't just want to use a formula and to substitute the formula. It's easy to read the question and substitute the formula in, right? And substitute the number in and say, oh, this and that, and substitute in, rather than bothering going through the long process like this. But I found this topic is really abstract, and it is hard to imagine the three-dimensional picture with on the curve, the revolving about the y-axis, the x-axis, right? So I try to put in this video to show you the concept of it. At least we get the general idea what shell method means and what this method means and what the differences between generation revolving around the y-axis, revolving about the x-axis for each technique, right? So I don't know. I try my best. I hope you enjoyed my video today and see you in the next video. Bye for now.